Welcome to a lesson on drilling on the lathe. This will be the sample piece for both our drilling operation and our boring operation. This video is just going to take care of this 1-inch through hole. So if you take a look in Mastercam, I already have the part drawn, the stock is set, so we can begin by selecting a drilling operation. Notice that we don't select any geometry. Again, with an operation like this, it's assumed that you're drilling on X0. There's no fancy live tooling operation with this particular operation selection here. So we had a 1-inch diameter hole in the drawing. It's a common drill size, so we'll take a look over here. Now, depending on what you have available in your turret, if you have an old high-speed steel drill, you might have to do step drilling and spot drilling, but we're going to assume that this is a U drill with carbide inserts. So I just want to try to find a 1-inch diameter drill. Look at that right there, 1-inch diameter. And tool number, let's say, I don't know, 10 in the turret. I'm pretty sure that's what we have in the shop. Again, double check before you set those numbers. I know in order to keep the machine from stalling, we've been working well at 2,000 per rev and 800 RPM. Again, I like to set a constant spindle speed, even though in this case with a fixed RPM it's irrelevant, but again, forming a good habit. Let's turn coolant on. Now if we had the option of doing so, we would turn the through spindle coolant on. That will have an effect on what operation style we pick later on. So let's go with through spindle coolant, and then I'll show you what operation we would pick in order to make this work properly. I'm going to do a force tool change, even though it's going to happen anyway because we used another tool in the previous operation. And I'll put in a comment, let's say drill through, let's say a size first, 1-inch drill through. Okay, so we have the tool selected, we have the tool number and offset number selected, we have a speed and feed selected, force tool change turned on, comments are filled out. So let's go to the next window here. And this looks a little bit like a drilling operation in a mill, if you're familiar with that window in Mastercam. I haven't covered that in a video yet. So you can select your depth, the style or the cycle that you're going to go by, the drill point calculation, clearance amount that you want to select. So I like to keep this really simple here. I always program to absolute depths with a mind for what we're dealing with in the engineering drawing. So if I know I have a 2-inch thick workpiece, you can see right here, I've made this front face X0, Z0. I want to drill all the way through a 2-inch workpiece with a drill that has more or less a flat bottom, which we'll get to in a moment. So if I just exceed that by a 1/4 of an inch or even an 1/8 of an inch, I know I'm going to get all the way through the workpiece from Z0. So if I go 2.125, it's an easy bit to remember. I don't have to keep in mind any kind of drill point tip calculation or anything like that. It's just an easy tack on an 1/8 of an inch or 1/4 inch, whatever is good for your application. Quick and easy, no additional steps. Pardon that noise, I forgot I had my, didn't have my alarms turned off. So again, -2 for the depth to the back face of the part. And then because it's a flat bottom drill that we're going to use, let's go -0.125. There, -2.125. And then I'm going to leave everything else alone here for the time being. Actually, no, we'll do a retract to absolute Z.1. That makes sure that once the tool, finishes drilling the hole, it will retract all the way out of the hole before returning to the home position. Excuse me. So then we want to select our cycle. So we can do peck drill, chip break, tapping operations, just like on the mill. But since we selected through spindle coolant, we want drill counterbore, where there'll be a constant feed in with no pecks and then a rapid back out, and that through spindle coolant will allow the chips to flush out the hole. So let's hit check and see what we have. Okay, so this gray line indicates the stock that is left over. Now remember, I said here with the depth of -2.125, that drill should be going all the way through the hole, but it's not, and this indicates that that drill has a more standard jobber drill point on it, probably 118 degrees. So just like in the grooving operation where we had to edit the width of the insert to get the proper size groove, we also need to make this drill reflect reality in the edit tool window. So again, I selected here, but the left click, or in the parameters, I can right click on the tool and say edit tool. Brings you to the same menu. So you have some freedom on how you manipulate this. window. So since I'm using a U drill, they have a flat bottom. So I can make this look like an end mill. This is an instance where I'm kind of lying to Mastercam. I know well enough that I can control these circumstances, and really this is just a graphic representation of the tool that I'm going to use. It's ultimately programming the speed, feed, depth of cut, operation type, using Coolant, and then actually picking the right tool in the shop that matters the most. So if I just represent a flat bottom drill using this end mill, that's a simple way to perform the task. So it's a 1-inch diameter drill. All the rest of these parameters could remain the same because we're not dealing with any lengths greater than 2.125. So if having a flute length of 3.75 is definitely adequate for this job and probably accurately represents the U drill that would be in the machine. So we have 2 flutes, everything's looking good there. All I did again was switch from drill that had 118 degree included angle to an end mill with a flat bottom, 0 degree angle. Or sorry, that's a 0 radius, never mind. And then I have a 1-inch diameter right here, green check mark, and now when I regenerate, you can see the hole goes all the way through. So if I go back into the parameters, and let's say you don't have through spindle coolant, you only have flood coolant. Or if you're using high-speed steel drill instead of a carbide drill, in which case, again, you would be using flood coolant instead of through spindle coolant. Then you would need to, pardon me, change your cycle type. So if you're using a high-speed steel drill, you would probably want to come in using a spot drill of some kind first and drill counterbore, and then come in with your 1-inch drill and a pec drill cycle. Or if we have a 1-inch carbide drill, but with no through spindle coolant, maybe we do something like a chip break with your flood coolant turned on here. So there is a pretty strong relationship between the coolant type that you select for this operation and the operation type you select, and it will have a great bearing on how well this performs, especially considering the depth that you're going to here. If you're drilling through a 1/2-inch thick workpiece, it will make a little difference. A carbide drill can dissipate the heat in a 1/2-inch deep cut most of the time just by using no coolant at all, but again, it depends on your material, all the work circumstances. I think that satisfies everything that you need to know about the basic parameters. So if you have any questions or comments or concerns about what you've seen here, leave something in the comments, and thanks for watching.